Today's lesson is going to be a continuation of use of calculus in kinematics for motion in a straight line. So last week we sort of did a little overview of how it works in general, and then we focused on the differentiation side of things. And today we are going to be focusing on the integration side of things. Okay, so just a reminder that all this is derived from a velocity time graph, which you can have a look at from last week's lesson if you forgot, or hopefully in your notes. But the bit we're focusing on today is integration. So if you have acceleration, if you integrate, you'll get velocity. And if you integrate that, you'll get displacement. And so if we are given functions for acceleration or velocity, then when we integrate them, we can find velocity and displacement. Okay, so let's jump into an example. So a particle is moving on the x-axis at time t equals 0. The particle is at the point where x equals 5. X is the displacement. Velocity of the particle at time t, where t is greater than or equal to 0. You just got to have that constraint in there because just think about common sense. We don't go backwards in time, but this isn't sort of meant to affect the question in any way. It's just being sort of crystal clear. So don't think that this is going to be part of the solution. So we've got it's 6t minus t squared meters per second. So that is the velocity at time t. So we're going to find an expression for the displacement after t seconds, and we have got to find the distance of the particle from the starting point when t equals 6. So we've got velocity, and we want an expression for the displacement. So quick reminder, you've got velocity, you integrate, and then you get your displacement. So we've got to integrate the 6t minus t squared. Seems pretty straightforward, but there's one little place that it could go wrong. So what we've got to do is you integrate, and you add 1 to your power, divide by a new power. You add 1 to your power, you divide by a new power. Don't forget the constant of integration. Okay, for part A, because it's an expression in terms of t, we can't just say the constant of integration is going to cancel out. So we've got to remember that plus c. And further than that, we have got enough information to work out what c is, because we're told at time t equals 0, the particle is at the point where x equals 5. So we can substitute in 0 for t and x for 5. So we've got 5 equals 3 times 0 squared minus 0 cubed over 3 plus c. And that way we can get that c equals 5. And then when you put the 5 back in here, you get your displacement of 3t squared minus t cubed over 3 plus 5. Now, a lot of the time, the constants of integrations will cancel, but in this instance, because it's just a general expression still involving t's, it didn't cancel, so we've got to work that out. That's the only place that could go wrong, really. Okay, so part B, the distance of the particle from the starting point. So we have got your 3t squared minus t cubed over 3 plus 5. If you put in 6 for that, you get out 41. It would be very tempting to say that's the answer, but it started at 5, which means that the distance from the starting point, the distance between 5 and 41 is 36 meters. So it's 36 meters away from where it started. Now, if the question was just part B, if we were given this initial information and we were just told, find the distance of the particle from the starting point, then what I would be tempted to do is just integrate this with limits of 6 and 0 and forget about this plus c, forget about working out the 5, and you get the answer of 36. And it's because the constant integration cancels out. But because of part A, we had that plus 5 on there, which means we've got to then take it off again for part B. So 2 little ways it could have tripped you up here, but hopefully that will make sense. So let's have a look at another example. So a particle travels in a straight line after t seconds. the velocity v meters squared is given by v equals 5 minus 3t squared. T is greater than or equal to 0, so that's just saying we're not going backwards in time. That doesn't really affect too much. It's just going to make everything crystal clear. It's not something to confuse you. I've seen people before now they've understood everything, but they're unconfident with their answer because they're like, well, I didn't use this t is greater than 0 anywhere. I don't know what that means. I don't know what I'm meant to do with that. Okay, so we've got to find the distance traveled by the particle in the third second of its motion. So third as in 3 little rd, second as in a unit of time. That could have been a little bit better worded, but it basically means how far does it travel between the second and the third second. So in that third second of time. Okay, so first thing's going to be draw a sketch for this. And it's perhaps not the most straightforward sketch to draw, but you should be able to do it. Okay, you've done graph sketching in UPure, you've done it at GCSE, and it is something that is going to be necessary. I'll show you the graph. I'll tell you how you should have drawn it and how you should have worked it out, and also why it's important to do so. But if you want to pause it here and have a go at doing it yourself, feel free. But otherwise, I'll show you the graph and how you are meant to get it. Okay, so this is what the graph looks like, and how you're meant to do it is the following. Okay, so know where it crosses the axes. Okay, where it crosses the y-axis, that means x is 0. So if you put in 0 here, you get an answer of 5. So that point there is 5. Then if you put in v equals 0, then you would get the answer 5 over the square root of 5 over 3. Now the square root of 5 over 3 turns out to be 1 point something. So it's not hugely important what that 1 point something is. The important thing is that everything we are looking for is beyond that point. So everything we're looking for is below the axis here. Okay, so we're not interested in this side of the graph because its t is greater than or equal to 0. You know it's going to curve down like this because hopefully you realized it's a negative quadratic. So that's one way of drawing the graph. Another way of drawing the graph would be to think about graph transformations. Think about your t-squared graph. It's going to look like a sort of a U shape here. Then minus turns it upside down. Your 3 is going to squash it in, and then your plus 5 is going to move it up. So you could think of it as graph transformations as well. But either way, you should end up with a graph that looks like this. You should realize that everything we're looking for is below the x-axis. Now, sometimes if it's a tricky question, they could ask you, what's the how far has it traveled in the first 3 seconds of its motion? And then I'd have part of the area above and part of the area below the axis, and that's going to be calculated differently. In this case, I can just integrate between 2 and 3, and it'll give me a minus number because it's below the axis, but it will tell me the answer, and I can just change the sign of it, and that's my answer. If I had to figure it out between 0 and 3, then I'd have to do between 0 and this point first, and then between this point and 3, and add them together, because otherwise, if I try doing between 0 and 3 in one go, parts of these cancel out and I get the wrong answer. Okay, so this is the hardest part of this question. Now it is just integrate it between 2 and 3. So integrate between 2 and 3, you get an answer of minus 14, and that gives you the final answer of 14 meters because we were expecting it to be minus, it's below the axis. That's another good reason why you should sketch the graph. It's because we were expecting a negative answer, we weren't surprised by it. A lot of people, if you don't sketch the graph, they get out an answer of minus 14, they think they've done something wrong, or they leave the answer as minus 14, which is wrong. and you can get into lots of different problems. Okay, so sketches are always going to help. Be careful if something is on both sides of the x-axis, you've got to work them out separately, and if something's below the axis, you've got to expect it to be negative. And the other point is knowing how to sketch these graphs. Think back to your pure work and think back to the previous example. We've got to be careful with the constant of integration. Sometimes it cancels out when we've got limits, but if you haven't got limits, if you're just looking for an expression, then it's not going to cancel out, and usually there's enough information to work out C. So that's all the examples for today. Okay, it's exercise 11D, which is attached in the assignment. I want you to have a go at that, and same as always, if you find anything difficult, message me about it, because what I'm getting submitted is lots of good work. It's people that understand it. You can hopefully check the answers in the back of the book, and you know that you understand everything. There's no point in me going over detailed explanations of every single question when you're getting them right. But what I'm not getting is work submitted from everybody, which means that I don't know if everybody understands. So it's up to you, because I can't just check over your work if you don't hand it in, to either hand in your work or at the very least ask me how to do certain questions if you're stuck with them. People have done it in the past and I've made videos for them. Okay, so that's everything for today, and I'll see you next time.